So, another day, another stream. Right. Hopefully, we'll keep this short, which never happens. But anyway, this one's going to be a little different. I'm basically not going to be talking a lot about Rust, or rather, anything about Rust at this point, because this is, you can just say some ramblings about the current state of GPU programming, or rather general purpose GPU programming. And I'm specifically, sort of putting my thoughts together on the AI ML space, where basically we're using GPUs, that is. How are things, in that space? What's going on? Who's doing what's state of the art, etc. So as you probably know if you've been watching my channel, I've pretty much been looking into this quite a bit, and these are just my thoughts. Let's just put it that way. So, and some observations, and I think maybe some predictions as well that might like to make. So yeah, I think that's why I think this should be pretty short. Again, hopefully. So let's just get started. General purpose GPU programming. When I use the word general purpose, it's not just limited to, let's say, AI ML. You've got scientific computing, you've got, aerospace engineering, you've got a whole bunch of other fields where you will need to use some kind of parallel processor, and the most dominant one right now is a GPU. There's, of course, things like ASIC accelerators, as they're being referred to, purpose-built hardware, things like Cerebrus, Grok, there's one more. Anyway, I forgot about it. So there's TensorTorrent as well, but TensorTorrent is doing a little, some hotcase stuff. Anyway, but effectively speaking, if you were to look at this space and you were to sort of limit your view to just how do you program, or you as a developer, how do you sort of develop software for this space, particularly the AI/ML space where you're talking about the need for parallel computing or parallel processing. So my question was, is this, is general purpose GPU programming actually generally accessible? And right now, as it stands, because because of the focus that AI ML has at this point, there's quite a lot of innovation happening in this space. And as you can see over here, predominantly speaking, the lingua franca right now for AI ML is Python, and it's sort of backed by C and C++ at this point. So those are the only two things. That's the first. I'm pretty sure everybody's noticed this, but I don't think a lot of people have actually put their heads to it. And that's kind of what I want to talk about over here as well. But before we get to that point, so in a nutshell, if you want to look at the AI ML space right now, you'd have, you'd want to go and look at it in terms of the compilers that are being used, because at the end of the day, it's not Python or it's not C++. It's code that's going to run on a machine, or the machine needs to execute some instructions. So you need to take code and you need to somehow get it into a form that the machine understands. So the job, and whose job is that? That's the compiler's job. So that's the way I look at it. Right now, there's a bunch of ways to do things. If you're working in this particular space, there's graph-based compilers, which I've talked about quite a bit. Some examples like PyTorch, TensorFlow, JAX, Apple's MLX, all of them sort of fall into that bucket. Of course, don't hold me to what I'm showing you on this, this calligraphy thing that I put together. these are good approximations because some of these frameworks and some of these tools, etc., have an overlapping range. They're trying to do more, they're trying to do less, etc. Does not matter, but this is the way I would categorize them for now. So graph-based compilers. In here, as you already know, I sort of talked about it quite a bit. You write your code in Python, and let's say you say, I want to do a matrix multiplication, or I want to do some kind of, I don't know, softmax or some other fancy thing that I want to do. I want to do an operation. The key point over here is you do not get to see you are not exposed to the actual hardware execution model. When I say the actual hardware execution model, I'm not talking about the host processor, which is the CPU. I'm talking about the coprocessor, in this case, which is usually a GPU. The GPU's execution model is very different from that of a CPU. GPUs prioritize throughput over latency. I've talked about all of that quite a bit. Also the execution model. So the primary difference over here is when we talk about graph-based compilers, you write your ops and then you convert that into a graph of ops, tree of ops, whatever you call it. And then you do an optimization, pass on top of that. And then you further lower it down into, some sort of IR. So all of these things, pretty much when we talk about compilers, they will have proprietary IR, that is intermediate representation, or they will have their own, they will have some level of standardized IR. But there's nothing, apart from NVIDIA, because it's the dominant force right now, apart from their IRs, pretty much everything else is a little bit in flux at this point. But just know that compilers, IRs are all involved over here in being able to compile, your Python code if it's a graph-based compiler. So you write your code in Python and then you construct a graph out of those operations, and then you optimize the graph, and then you go ahead and produce machine code, which is called a code generator. So basically ops directly to GPU kernels, which means the graph-based compilers are effectively sort of leveraging, native compilers. So for every op that you write, not every op, but because if you have operator fusion going on, you're probably going to like fuse a bunch of operations together and get some performance speed ups out of it. But anyway, for a bunch of operations usually get mapped to some GPU kernel written in the native, GPU frameworks, and they get launched onto the GPU. So that's one way of looking at things. Then the second one is domain-specific languages. Now, pretty much every domain-specific language that exists out there, at least for, let's say, the AI world or the ML world, is Python. It's a language that's embedded in some kind of Python. So you'll see this being called out over and over again. So one of the most famous ones is Triton. This has the lion's share of attention at this point, and there's a lot of folks that are building off of it. For example, Gluon itself is by the same guys, but it wants to be a lower level version of the tile-based DSL. I'm not going to go into, if you're wondering what tile-based is, you can probably watch some of my other streams where I talk about the hierarchy of computing in GPUs. You have a thread, then you have warps, or that's CUDA terminology, but you'll have a collection of threads that execute in lockstep. That's usually called a warp. And then you'll have multiple warps sort of batched together, which is usually a block of threads. And then you've got, a grid. And then there's one more piece that was recently added in the newer architectures, which is something that I will talk about as well, called a thread block cluster. That's also something that sort of pops in. So these languages primarily are tile-based DSLs. That means so the first thing I want to say is no exposure to the hardware over here in graph-based compilers. Of course, if you actually go and talk to a PyTorch, expert, etc., they'd say, no, you can write custom CUDA kernels, etc. Yes, true. I'm not looking at that, that portion. I'm just saying in general, graph-based compilers work this way. And then you've got your tile-based DSLs, which expose some level or some portion of the hardware execution model. And that's why I said, block or grid level, computing hierarchy is exposed to you. And then the other one is, by the way, QTile is from NVIDIA. Tilelang, I believe, is from Microsoft. Not sure, it's been a while since I looked at them, but I assume that is the case. Lower level DSLs like Gluon, this is up and coming. TLX is from Meta Research. Again, this is a language extension to Triton itself. So both of these are actually Triton based, all right? But it's just that I don't want to only be doing block and grid and sort of limit myself to that. So here's the point. The level of abstraction keeps increasing as I go from left to right. All right, the level of abstraction actually keeps decreasing. You try and expose more of the hardware as we go from left to right. That's what I'm trying to say. When you go to these lower level DSLs, especially CUDA, which is something directly from NVIDIA itself, it's trying to take something like Cutlass, which is CUDA templates for linear algebra subroutines. Cutlass has been around for a while. It's basically a layer that runs on top of CUDA itself, and you get full exposure to the hardware, but primarily focused on linear algebra stuff. So basically, if you take something like a matrix multiplication and optimize the heck out of it, you get Cutlass. It has other things like compile time, specialization. It's a template library, so in C++, so it's heavily compile time based and specialized, etc. So that's one option. And this is where most of the hardware is exposed. The execution model of the hardware is exposed. You've got all 4 levels of the thread and memory hierarchy, which means thread stuff that I already said, which is you've got your individual threads of execution, your what you call your warp or your collection of threads that execute in lockstep, and then your block of threads, which are a bunch of warps that are organized in a block, etc. And then you've also got the grid. But before the grid, you have something called a thread block cluster, which is the new concept that NVIDIA introduced. That's also accessible to you from CUDA. Along with that, pretty much the entire memory hierarchy is available. The L1 caches, the L2 caches, the shared memory stuff, the registers, and the global memory piece. All of them are pretty much accessible to you. There is an asterisk over here because some of this, I'm yet to come across a concrete example, but I've heard in many places it's not exactly CUDA, which is this stuff, which means CUDA was written to provide complete full access to the hardware that you're going to be using. So whatever GPU you're going to be using from NVIDIA, CUDA provides full access through, NVCC. Obviously, there are LLVM alternatives to this, like Clang, etc. But fine. So yeah, that's the Python world. You've got the graph-based compilers, and then you've got the DSL stuff. Pretty much all of this is a DSL. And that's sort of what this is looking like. And a lot of innovation is happening in this space, especially Triton. And obviously it's I wouldn't say it's forks because these are actually much lower level stuff, but extensions to, let's say, Triton. There's a lot of interest and there's a lot of push behind that, but it's all Python at this point, right? And the other point is the reason, for example, these graph-based compilers inevitably leverage native compilers to do the actual compilation of GPU kernels. These don't necessarily do that. They're built on their own compiler stack, For example, a lot of these things are actually built on MLIR. At least Triton is, ThunderKittens is. CUDA, I'm not sure, but anyway. So sorry, CUDA is not. It uses NVIDIA's proprietary IR, which I believe is going to be open sourced. I'm yet to see that. So that's what's going on. And then same thing. These are extensions of this. So yeah, this is built on Cutlass. This is embedded in Cutlass. These are two built on Triton. So MLIR is going to be expanded a bit more for you to expose more of the hardware, etc. When I keep saying expose more of the hardware execution model, if you were to just think about it simply, you can just say you are exposed to more of the hardware instruction set that's available to you during programming, right? Some of this stuff, usually the compiler optimizes away. It happens automatically. Things like memory coalescing, shared memory management, scheduling, a lot of different things just happen, right? Where the compiler does it for you. No, if you don't want that to happen, if you want control over that because you're doing something hotke, so that's when you reach out to this. So at this point, at least for CUDA, DSL and this stuff, I haven't seen much of a difference. So you get most of the power that you'd get when you reach down into the C++ CUDA stack directly in an embedded DSL in one of those in Cutlass, right? So that's the closest thing that I've seen where you can use a higher level programming language to sort of get the same kind of performance. Great. So that's where we are. But native compilers, as they are, NVIDIA's CUDA uses NVCC, ROCm has HIP-CC, which is, I keep forgetting that, heterogeneous, interoperable, blah, 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 whatever, something. Okay. Apple's Metal compiler, which I'm not a big fan of. There's so much potential here, but sorry, it's just limited. There's a myriad number of SPIR-V compilers that I've covered, including Rust. The Rust folks are working on the Rust GPU project, which is Rust to SPIR-V basically. And I actually put Mojo over here because Mojo was, many people consider that a domain-specific language, and I'm like, not really. Firstly, it's a general purpose programming language. You can pretty much write any kind of software that you want, not just AI/ML software. But the fact that these guys are really going for, optimizing the hell out of it for the AI/ML world, sort of can make people think that. So technically speaking, it's in the right place. The thing about these things, I haven't included things like Intel's DPCC and Level 0 and all of that stuff. But anyway, all of them provide full access to the hardware with which you're working. If it's an NVIDIA GPU, NVIDIA, AMD, Apple, whatever. Okay? And Mojo is, right now I believe they support AMD and NVIDIA, and they've been publishing some blog posts about, them beating the current implementations of cuBLAS, etc., in terms of at least matrix multiplication. That's great. So my first observation is, it's great. There's a lot of innovation happening. There's a serious effort to actually weigh the costs of productivity. Let me just stop this blinking stuff. To sort of make the developer more productive versus, the control and power that you get. Because trust me when I say this, regardless of what model you're building, 95 to 99% of your effort is not going to go to, really figuring out how to get CUDA to work, etc. You already know what you're going to be doing to get that, to eke out that performance. The 1-2% at a massive scale really costs a lot of money, which is where, you want to figure out if there's an easier way to do things. At least that's my take. But inherently, you should have noticed something by now. Python and C++, there's nothing you can say GPU specific about these languages. They're just general purpose programming languages, like any other language. C++ is feature loaded. It's got a lot of stuff. Python is extremely useful or extremely easy to prototype in. And that's kind of what gave it the edge. And that's why the entire ML community sort of, gravitated towards it, primarily because of the timing and the usability and a whole bunch of other factors that led to it being, the dominant language in this space. But from a technical standpoint, why X versus Y, there's not really much, all right? That's the key point. So the only thought that occurred to me was, if it's just compilers that we're talking about that we're actually really working on, we're layering, front ends on top of them in the form of Python or in the form of C++, like Cutlass, etc. Why are we just limiting ourselves to a language, like these two, right? As much as it pains me to say, we should generally go ahead and open it up to, let's say, I don't know, a JavaScript developer. Open up the GPU execution model to, say, a JavaScript developer. This has already happened in the sense with web GPU. That's already happening. Now, of course, it's not, it's web GPU is focused primarily on rendering, if you ask me. The compute stuff is there, but you really can't do whatever I'm going to talk about right now. Let's say you want to write the most performant generalized matrix multiplication kernel. That's really not possible in web GPU, at least at this point. So if we can say take CUDA and expose it to any language, that would be killer, right? So that's kind of what I'm interested in at this point, and I sort of am looking at all these options out there and trying to understand, is there a blocker actually from introducing the full execution model of the hardware to pretty much any language, not just these two, thereby co-opting all of these large developer communities that have been built out that primarily only write software for the CPU at this point. The reason I say this is because today GPU or accelerated computing is pretty much getting to the point where it's going to rival that of writing software for general purpose processors like the CPU. It's pretty much getting to that point, and I actually foresee that happening in the next couple of years actually. So it makes sense to pull in all of these other developers. I don't know, just Python's interpreted, JavaScript, Go, Rust, blah, whatever, put a name in there. There's already people that are working on this in multiple scenarios, across multiple ideas, I'd say. Rust ecosystem is one big one. There's a huge push over there from different corners of the ecosystem to actually go ahead and sort of work with, accelerated or accelerators or GPUs directly from Rust. And I've talked about them at length in many, many videos. Likewise, I believe there's a bunch of options in every single, developer community. And I think thinking along these lines may make a lot of sense rather than limiting ourselves to one front end. To me, at least, all of these languages are just front ends for you to work with, your compilers. You pick your level of abstraction and then you go ahead and make one. But just opening that compiler up and making it easy to sort of work with other languages is the key problem, is the way I'm thinking about it. Yep, please feel free to drop a comment or thoughts if you think yes or otherwise. So just to drive home that point, I was trying to look at, I've looked at these kernels quite a bit, and there's actually, let me just So there's a bunch of blogs out there, which I'm not going to like go through each one of them. There's a blog by Simone, let me find him. Simone, GPU. Yeah, CUDA. So this is pretty much the first hit that you're going to get if you, yeah, sorry about that, bright stuff. Let me put it back. Yeah, you're pretty much going to get, you know, this person's blog, and he's written a work log of how to optimize MATML for, you know, to sort of get NVIDIA library. So ClueBLAS is this thing for folks who don't know. It's like a precompiled library that's available to you from NVIDIA, where NVIDIA optimized the hell out of it for its hardware. You pretty much can, you know, go above it. Theoretically, you can't. In some places you can, like you can get a couple of points here and there, but that's about it. The thing that this blog talks about is how do you get to that level of performance by yourself without having to leverage ClueBLAS, right? You might be wondering why. Somebody already wrote it. Let's not get in there. There's a whole bunch of reasons for why. But anyway, so there's this blog, but this is a little old because this was written in 2022. 2022 is old, okay, in AI terms. So there's this blog by Pranjal. I don't know the last name, so I'll just say Pranjal. And he sort of built on top of Simon's blog itself and pretty much did the same thing where he writes, let me see. Okay, this is the problem. That's why I don't like. Wait a minute. Why am I doing that? Hey, what happened to this? Okay, I don't know. My browser's acting up. Just give me a minute. Yeah. See, sometimes you just need to switch browsers. So he basically goes through a blog, and there's another one. I think I was talking to you about that, which is the Mojo folks have sort of written their own blogs about how they've done the same thing, which is optimize the heck out of their matrix multiplication kernels to beat something like ClueBLAS, etc., and do better than that. Well, I'm not going to go through everything. You can just read the blog for that. Just want to drive home a point saying there's nothing really in the languages that the developers themselves are currently using, because they're trying to target an execution model based on what's available to them. So if I use a particular piece of hardware in the, in NVIDIA's GPUs, I get an X amount of performance improvement. If I go ahead and use a particular paradigm, like what's called a producer-consumer paradigm, I'm going to get another X. So you're actually writing software for the exact hardware, right? And this is another problem, by the way. So the moment the hardware changes, your old kernels are not really just going to be portable onto the new one. And that's, there's a big, there's a big industry that's being built around that itself. But anyway, what I was trying to say is the front ends, though the languages that we use to actually write the software as the developer that we sort of work with, that's not the ones that, should be important. And if we put in a little more effort, I think we can go ahead and expose this and pull in the entire developer community that currently writes software, all kinds of different software for the IML world, right? It's not going to be easy because working with the compiler and making it easy for somebody to bring over their language is going to be a little difficult. But I've seen this with what's happening in the Rust world, where they've been targeting, for example, CUDA. They've been targeting NVIDIA, which is NVIDIA's intermediate representation. All right. So you target that, and then you go ahead and produce your CUDA binaries. Likewise, there's a bunch of options available to you that you can go ahead and do this and not really rely on just, 2 sets of communities, which are great. There's no problem with that. We should continue doing that. But bring in more so that, considering where we're going, I think this is going to be the next big space for developers. We're going to need them. That's the way I'm seeing it. We're going to need a lot more people who know a lot more about this. And the best way to do it is to actually really meet them where they are and not have them, really learn a new domain-specific language, because the number of times I've actually seen domain-specific languages being, crafted only for them to become really niche and, used by section A or section B, etc. That's happened multiple times. It's usually the case that if you can make it easy to work with what you already know, that's the biggest bang for your buck that's my thinking, at least. So just to sort of drive home that point, this blog, I'd highly recommend it. So please read it. I'll probably leave a link in the video description. So I'll just sort of talk about the bigger picture of it. You're just doing basic matrix multiplication, and you might be wondering, okay, if you know nothing, for the uninitiated, about how much goes into optimizing a matrix, a matmul, watch. This is just, the top 10%. There's a lot more that I'm not going to be covering. So effectively speaking, when we look at matmul, we're saying, there's this m by k matrix versus this n by k matrix, and I want to basically multiply these two. So that should produce this, right? So this, you might be wondering if it's small, we are really not going to see any benefit if you run it on the CPU versus the GPU. But if these things get large, then, the GPU really comes into its own. And the way that actually works is, when you want to do something like this, you first have to go look at the architecture, the GPU architecture. The way the GPU architecture, pretty much every GPU, this is not just NVIDIA. This is what they look like. The naming convention is going to be different, but they'll have the same stuff in there. For example, you'll have compute units instead of SM1s in AMD's case. You'll probably have, wave fronts instead of warps, which is the collection of threads. Same things, but different terminology and subtly different inner workings, maybe. But pretty much, it'll look like this. So let's say you take the H100 GPU. It has like 3 levels of caching, at least. You've got high bandwidth, which is the global memory. That's your VRAM, as it's called. Then there's an L2 cache, which is the next cache layer. This is not programmable. But then the one above this, which is called shared memory, or an L1 cache, this is programmable. This sits inside the SM. In the SM, you basically have, your ALUs, the ones that actually do the compute, etc. You also have these things called Tensor Cores, which is an addition, a recent addition in some previous generations. I don't remember which generation started it, but right now, this is the heavy lifter. These things can do petaflops of compute. Petaflops. Okay? Just keep that in mind. So this is the model, or this is the hardware architecture, and you're supposed to use all of this to eke out the maximum performance that you want. Right? That's what optimization is. All right? And it's not a language specific thing. Of course, because of years of investment going into a particular direction, you might wonder that maybe this is it. But at least think about the front end. The front end doesn't really need to be X, Y, or Z, right? So the first thing is this. And then I'm just going to cover a few pieces. So what happens if you want to do a matrix multiplication like this? Let's say you have your matrix in global memory, which is this memory, okay? You have this matrix in there. you can't pull this entire matrix into this smaller shared memory because it's much smaller. This is like gigabytes and this is like kilobytes, right? That's not going to work. So you tile it up, basically subdivide it into some chunks. These are called tiles. Now you remember when I talked about tile-based DSLs, they operate at this level of an abstraction. And then you pull them in here, and then you go ahead and, so effectively what's happening here is, at least let me see if I can show you. This is a nice diagram that I saw. Yeah, here's what happens. You pull one tile into shared memory, and in order to do that, there's a piece of new hardware in NVIDIA's GPUs called the Tensor Memory Accelerator. You know, it's there. You don't have to, like previously before this was available to developers, they had to go ahead and actually write some code to be able to load, you know, data into shared memory. And if you know by now, if it's already struck you, the single biggest bottleneck in accelerated computing at this point is data movement. That's data movement within the chip and data movement between, you know, accelerators or GPUs. So in both cases, the biggest bottleneck is data movement, and the entire thing that I'm going to actually whatever I'm going to walk you through is going to be focused on that part. Compute is not actually that big of a problem because there's a lot more compute available to you. It's just that we need to get that data into that compute layer, that is. So yeah, so the first thing is you basically break your matrix up into tiles, and then you load a tile into shared memory because this is much closer to your compute units. And the way to do that is you use a dedicated piece of hardware called TMA. This thing actually takes care of, I'm not going to show you the whole thing, but this thing actually takes care of, where is that? Nope. So, nope. I showed you that. Sorry, yeah. So if you're wondering, okay, just a data copy, how hard can it be? No, you're going to need to provide an exact tiling configuration with a bunch of different ways you can actually go about tiling it. There's things like swizzling, interleaving, you know, data types, the shapes and sizes, strides, a whole bunch of things that you need. So what do? NVIDIA comes out and says that we're not going to reinvent anything. Let's just create a descriptor. In this case, this is actually, in simple words, a memory descriptor saying, here's how your data is laid out in memory. Go ahead, do the copy. All right, I'm going to give it to you. And the hardware is going to do it. The TMA accelerator will do that. So you need to provide this TMA descriptor and, you know, call a specific function like, you know, so. You basically call something, this is from CUDA. So the entire implementation, that's Pranjal's implementation, is basically leveraging CUDA. And if I was to show you, this is what it will look like. So where's that? Okay, let me just go to the bottom. So yeah, see, we're basically going to allocate memory in shared memory, and then we're going to create the tensor map. The tensor map creation happens here, where it calls CUTensor map encode tiled, blah, whatever. It's something that's available to you as part of the CUDA SDK. You can go ahead and leverage that to do your thing. Yeah, it's C++. So yeah, I need strong typing. I really need strong typing. This is not a good thing for me, at least. Okay. Anyway, so that's that. Just doing that, because you're actually just entrusting hardware to be able to do your loads, gives you a certain boost. But you load into shared memory and do what? You actually leverage what are called these tensor cores. Let's say, yeah, you leverage these tensor cores to do the matrix math, because these things, the dedicated matrix, multiply and accumulate, you can say IP that's present in the chip. That's all they do. There's no other fancy arithmetic that they do. They just do matrix math, and you're using the Tensor Cores to actually push that in there. So that's kind of what is being said over here. The Tensor Cores are a little more versatile. I'm saying they're not just simple Tensor Cores. They can do different kinds of, matrix math. For example, this is an instruction. This is an instruction that is used to, tell the GPU, say, use the Tensor Core and do where M is of dimension 64, N is of dimension 16, and K is of dimension 16. When you get that, go ahead and ensure that the output is in F32 and the inputs are BF16. So, and then you can, if you read this is MMA. The WG stands for warp group, which is a collection of warps, which is 4 warps. But anyway, so this instruction is what you issue so that you can leverage the Tensor Cores, right? That's it. So in order to leverage these Tensor Cores, you first need to put the data in shared memory, right? And in order to do that, instead of doing it manually and trying to figure out how you can do this, how you can do the loads as fast as possible, you now have a dedicated piece of hardware, not just for the compute, which is tensor computation. You also have for memory load itself, right? So those two things combined, if you were to go ahead and do them, you would be, where was I? You'd sort of see, that you've reached 317 teraflops, which if we go up here and go back to all the other optimizations, you see that QBlast by itself can deliver 716 teraflops for the same workload. That's what we're benchmarking against. The previous algorithms before, whatever I showed you right now is something that's part of Hopper, I believe. That's where this came into picture, the Tensor Memory Accelerator and the faster Tensor Cores, etc. You already get to this point, 317. That's a 44% jump, right? And likewise, if we keep going further and doing all these other optimizations, we will hit this number. This is 716. You can hit 763 teraflops. That's what this blog is trying to show you. Okay. So the important thing that I want to make, I want to sort of talk about is there's really nothing about the front end. Again, the languages that you're using to write this stuff in. This is general C++ that you can use. Of course, it's heavily templatized in the sense a lot of generics are being used. But at the end of the day, if you actually go and look at the real kernel, you'll see that this is it. You'll see, okay, where is that? This is the kernel that's actually going to be running. It's global. It has some launch bounds. All that's not important, but this is the kernel that we're running to basically do the matmul. And we're starting off 2 barriers. This again is a new piece that was introduced in Ampere, where so rather than me talk about that, let me just show you what that is. So like before the Ampere architecture, that's Pascal, Volta, Turing, etc. You had like a single barrier, basically a synchronization primitive that you use so that all threads in your, that you're using to perform a certain computation can synchronize, right? And that's a little more coarse-grained. What you wanted was a little more fine-grained. So they basically took a synchronization primitive and said, let's, decouple the completion of work and the waiting for the next piece, like waiting for all the other threads to also do the same thing. Because if you can do that, you can actually micro optimize over there to say, maybe this thread can go do some other work, right? Everything's about latency hiding over here. As much as possible, that's what the GPU is being heavily optimized for. That's what all the major players are optimizing for. That's the focus of a GPU. So that's called a split barrier. Again, you leverage that. You leverage faster barriers. You can use the barriers in such a way that you can get some level of speed up. So that's something that can happen. So effectively speaking, let me just talk about the last piece over here. Where is that? So in this simple kernel, to the point where we went from 30 teraflops per second to 300 teraflops using the Tensor Cores, all we're doing is we load a single tile into shared memory. We perform the computation like we do over here. The WGMMA 64. We perform the computation over here. This thing is actually calling, inline assembly. And throughout CUDA, you're going to find this. Like if you go actually look at the implementations, it's all going to be, it's also going to be a lot of very specific instructions that you want invoked, and you want to use them directly, all right? So that's the first thing. So you load a tensor. So you load a tile into shared memory. That's A and B over here. And then you wait for them to be loaded. That's what the barrier synchronization does. And the moment everything is synchronized over there, you go ahead and issue your compute, instructions. And then you wait for the compute to be done. And then once that's done, you go ahead and store the result back in global memory. But before storing in global memory, you might be, when you're issuing 4 of these, etc., the intermediate results are actually held in registers. So that's pretty much what you're doing, which is what the legend over here shows. You load, you compute, and then you store. The store only happens once, but load and compute sort of are interleaved. So the moment you start to look at something like this, you can easily say, hey, wait, you know what? The load and the compute can probably overlap, right? I can possibly go ahead and say, while I'm loading some new stuff, I can probably be computing, so let's say I loaded 5 tiles. Then I can go ahead, instead of loading just a single tile, I can have the compute, I can have a bunch of threads work on the compute part of the problem. And then, some other threads work on just the loading part, right? I can go ahead and do that. That's where, you immediately come across an idea where, it's called producer-consumers. Basically speaking, a producer-consumer is something that you already know. It's a shared queue. In GPU memory, you're going to create a shared queue in shared memory that says, okay, instead of 1 tile, I'm going to throw in 5 tiles, and you keep consuming those tiles, I'll keep filling in those tiles from the other end. Obviously, this is going to require some more synchronization, some extra synchronization stuff, where instead of a single barrier, you're going to have 5 or 6 barriers, depending on the size of your queue, etc. And then you're going to synchronize for all the compute threads that are going to be consuming the work, right? So inherently speaking, there's nothing very specific about any language, right? Any front end. It's about programming to the metal, literally programming to the metal. And the most important thing over there is going to be being able to generally access that hardware. Bring in all, the larger developer pool, because Python is a big one. C++ not as big, but you've got massive developer communities that could probably be introduced to this execution model. And we'd be able to really pull in a lot more folks into this space. That's been on my mind for quite some time. And So I've sort of alluded to this on and off in some of my streams, etc. But yeah, I think this is where we should be heading, or we're probably headed, maybe. So yeah, so this is what I thought. These are just my thoughts. That's why I call this ramblings. But yes, the hardware it's all about what level of access do you want for the hardware, and making it accessible, making it generally accessible to the wider developer communities that are out there, rather than the limited ones right now. For example, I certainly believe Apple should be thinking beyond just the metal shading language. All right, because I've heard from so many folks saying, okay, I really love to do it, but I don't think that's my forte. It's not really. If you just expose the hardware execution model, simplify it in such a way that, and I don't believe even, the vendors themselves who make the hardware actually have to put in all the work. You just need to make it easier for people to be able to leverage your compiler infrastructure and your compiler IRs, right? That's the starting point, at least. Anyway, so that's sort of what I want to talk about. There's a whole bunch of things, just matrix math alone. You can just jump into these blogs and you can talk about how much you can optimize them. So, for example, just to give you some more stuff that's now available in Hopper itself, I believe. So let me just go back to, the blog. So this is the shared queue stuff. Let me see if I can find it. There's warp specialization, which is what you would use if you're using the producer-consumer model. Storing latencies, no. Okay, so I don't see the stuff over here, but basically, let me just go to the top. If you go back to the diagram where we talked about the hardware architecture, so the fundamental limitation in pretty much all the previous architectures, I believe up to Hopper, I don't know if it's Hopper or Blackwell in NVIDIA, was that you couldn't really share, this shared memory of one SM wasn't really accessible to, this other SM. They were like independent of each other. So you had to like partition your work and distribute that to both SMs so that they do the work, and then you get it back and then you fuse that, whatever results you've got. Now what's happened is you've got things like distributed shared memory. That's fundamental separation in terms of the architecture itself. You're adding a new component to it. Now that needs to be exposed as well if you want to be able to use that. All of these things are what we've been getting in successive iterations of hardware that's being put forth, or architectures that are being put forth. And I sensibly think now is the time to actually, before this gets way too complicated and way too much investment is spent on just the two pony horses, open it up to a lot more folks by leveraging the compiler stacks that they have itself and sort of finding ways to bring in a larger developer pool, right? That is something that I most likely think it's possible, and I see that happening in the Rust world. I wish it happens across the board, right? Because there's going to be so much more folks who get involved in this and are able to leverage and add to this. I firmly believe in that, at least. So so that's I guess that's sort of what I want to talk about, just some general thoughts as such. I'd love to hear thoughts. I don't think there's any feedback, but any comments and thoughts, please let me know. All right, that's about it from my end. Have a great day. Thank you.